Right now, as you watch this, you're convinced you're real. Your fingers feel the device in your hands. Your eyes process light bouncing off a screen. Your brain transforms electrical signals into thoughts. But what if I told you that everything you've ever experienced, every sensation, every memory, every moment of consciousness might be nothing more than code running on some unimaginably powerful computer? You've felt it before, haven't you? That strange moment when you walk into a room and swear you've lived this exact scene. Already, the word on the tip of your tongue that vanishes the instant you reach for it. The friend who insists a movie quote was different than you remember. So different that you question your own memory. These aren't just quirks of human psyche. They might be glitches. Consider the Mandela effect, where thousands of people share identical false memories of events that apparently never happened. Why? Would our brains manufacture the same fictional details? What if these aren't false memories at all, but remnants from a previous version of our reality? Digital artifacts left behind when the simulation updated. The idea sounds like science fiction, but here's what should terrify and fascinate you. Some of the world's most brilliant minds are taking this possibility seriously. Elon Musk famously declared the odds we're living in base reality as billions to 1. Philosophers at Oxford are publishing papers calculating the probability that we're simulated beings. Tech billionaires are reportedly funding research to break us out of what they believe is our digital prison. But why now? What's driving this sudden concern that reality itself might be counterfeit? The answer lies in our own technological trajectory. Every 18 months, our computing power doubles. Virtual worlds become more realistic. Artificial intelligence is more sophisticated. If this exponential growth continues for just a few more decades, we'll possess the ability to create perfect simulations, entire universes indistinguishable from reality, populated by digital beings who believe they're flesh and blood. Here's the disturbing logic. If such simulations become possible, they'll likely be created in vast numbers. Millions, billions, perhaps trillions of simulated worlds, which means simulated beings would vastly outnumber real ones. Statistically speaking, you're more likely to be artificial than authentic. The evidence for this possibility comes from the most unexpected places: quantum physics, computer science, even ancient philosophy. And once you see it, you can never unsee it. 2,000 years ago, a Chinese philosopher named Zhuangzi fell asleep in his garden and dreamed he was a butterfly. In the dream, he fluttered from flower to flower, completely absorbed in his butterfly existence, with no memory of being human. When he awoke, Zhuangzi faced a terrifying question. Was he a man who had dreamed of being a butterfly? Or was he actually a butterfly, now dreaming of being a man? This wasn't just poetic musing, it was perhaps humanity's first rigorous examination of reality's nature. How could Zhuangzi prove his waking life was more real than his dream? Both experiences felt authentic while he lived. Them both contained sensory details, emotions, coherent narratives. The only difference was which consciousness he happened to occupy at any given moment. 15 centuries later, René Descartes pushed this dilemma even further. Sitting by his fireplace, he imagined an evil demon with unlimited power, capable of deceiving him about everything. What if this demon fed him false sensations, phantom warmth from a non-existent fire, the illusion of hands that weren't there, memories of a life he'd never lived? Descartes realized he could doubt everything, except one thing, the fact that he was thinking. I think, therefore I am became philosophy's most famous declaration. But it also revealed something unsettling. Thought might be the only thing we can truly know. These ancient insights weren't isolated curiosities across cultures. Brilliant minds independently arrived at the same disturbing possibility. Hindu philosophers described Maya, the cosmic illusion that veils reality's true nature. Plato's cave allegory suggested we mistake shadows on a wall for reality itself. Buddhist teaching speaks of the world as fundamentally empty, a projection of consciousness, rather than solid matter. But here's what's remarkable. These weren't just philosophical exercises. They were systematic attempts to solve the same puzzle that haunts us today. Our senses can be deceived. If our memories can be false. If our entire experience of reality depends on the reliability of our consciousness, then how can we ever know what's truly real? The question gained new urgency during the scientific revolution, as telescopes revealed that our senses deceived us about the heavens. The sun didn't actually revolve around Earth. Philosophers wondered, what else might be illusion? If our most basic perceptions about the universe were wrong, what foundation remained for certainty about anything? This skeptical tradition wasn't academic navel-gazing. It was rigorous intellectual preparation for a shocking possibility. That reality itself might not be what it seems. These philosophers were developing the conceptual tools we'd eventually need to seriously consider that we might be living inside an artificial construct. Consider the parallels. Zhuangzi's butterfly dream mirrors our modern concern about simulated experiences that feel authentic. Descartes' evil demon resembles today's speculation about advanced civilizations creating false realities. Plato's cave dwellers mistake projections for reality, just as we might mistake digital inputs for physical sensations. The ancients lacked our computing metaphors, but they grasped the fundamental issue. Consciousness creates our reality, and consciousness can be fooled. They understood that the question, what is real, has no easy answers. When everything we know comes filtered through potentially unreliable senses and minds, this philosophical groundwork proved prophetic. When 20th century scientists began discovering the bizarre nature of quantum mechanics, particles that exist in multiple states simultaneously, observations that change reality, information that travels faster than light, they found themselves returning to these ancient questions. With renewed urgency, the dreamers and skeptics of the past weren't just asking hypothetical questions. They were preparing us for the possibility that reality's nature might be far stranger than we assumed. And as our technology grows more powerful, Their ancient warnings are starting to sound less like philosophy and more like prediction. In 2003, a Swedish philosopher named Nick Bostrom sat in his Oxford office, staring at an equation that would reshape humanity's understanding of existence itself. Bostrom wasn't your typical academic. He was obsessed with humanity's future, spending his days calculating the odds of our survival, the potential for artificial intelligence, and the strange possibilities that emerge when civilizations grow powerful enough to reshape reality. That year, Bostrom published a paper that would haunt Silicon Valley executives. Inspire Hollywood blockbusters and force serious scientists to confront an uncomfortable question. What if we're not real? The paper was deceptively titled, "Are You Living in a Computer Simulation?" But Bostrom wasn't asking this question casually. He was a philosopher trained in formal logic, someone who built arguments like mathematical proofs, and his proof led to a conclusion so unsettling. Even he seemed surprised by its implications. Bostrom's genius lay in recognizing that simulation theory wasn't really about technology. It was about statistics. He constructed what philosophers now call the simulation trilemma, a logical trap with no comfortable escape routes. According to Bostrom, at least one of three statements must be true, and each possibility is deeply disturbing. The first possibility, advanced. Civilizations never developed the computational power to run realistic simulations of their ancestors. This seems increasingly unlikely. Our own computing power doubles every 18 months. Video games already create photorealistic worlds. If this exponential growth continues for just a few more centuries, we'll possess computational resources that dwarf anything in existence today, assuming we don't destroy ourselves first. There's no obvious barrier preventing us from eventually simulating entire histories. The second possibility, advanced civilizations develop this power, but choose not to use it. Maybe they find ancestor simulations boring, or perhaps they consider them unethical. But this assumption requires every advanced civilization to make the same choice. Think about human nature. When we gain new capabilities, we tend to use them. If civilizations can create simulated beings, some will, even if most civilizations show restraint. It only takes one to create billions of simulated worlds. This leaves Bostrom's third possibility, the one that keeps philosophers awake at night. Advanced civilizations do create ancestor simulations, and we're almost certainly living inside one. The logic is brutally simple. If simulated beings become possible, they'll vastly outnumber real ones. Imagine a civilization that creates 1 million ancestor simulations, each populated by billions of conscious beings. Suddenly, for every real person, there are billions of simulated ones. You're far more likely to be artificial than authentic, not because there's anything special about you, but because simulated beings would dominate the population statistics. Bostrom called this the bland principle of indifference. From your perspective, inside the simulation, everything would feel perfectly real. You'd have no way to distinguish your artificial existence from an authentic one. the simulated pain in your stubbed toe would hurt exactly as much as real pain. Your simulated memories of childhood would seem just as vivid as genuine memories. Your simulated consciousness would be indistinguishable from the real thing. When Bostrom published his paper, most academics treated it as an interesting thought experiment. But something unexpected happened. The people building our technological future started taking it seriously. Really seriously, Elon Musk declared, "The chief odds we're living in base reality as billions to one against." He wasn't joking. Musk has reportedly invested in research aimed at detecting evidence of our simulated existence. PayPal co-founder Peter Thiel has funded similar investigations. Tech executives who spend their days creating increasingly realistic virtual worlds apparently find simulation theory quite plausible. But here's what makes Bostrom's argument so unsettling. It doesn't depend on any speculative technology or far-fetched scenarios. It only requires three modest assumptions: that consciousness can be simulated, that advanced civilizations will have enormous computational resources, and that at least some of them will choose to run ancestor simulations. Each assumption seems reasonable, even conservative. The trilemma forces us into an uncomfortable position. We can believe that every advanced civilization throughout the universe will either fail to develop sufficient computational power or unanimously choose not to simulate their ancestors. Or we can accept that we're probably digital beings, living out programmed lives in someone else's computer. Bostrom himself doesn't claim to know which possibility is true. He simply demonstrates that one of them must be. His paper doesn't prove we're simulated. It proves that the question deserves serious consideration. And that mathematical proof, published in a respectable philosophy journal, transformed simulation theory from science fiction speculation into legitimate academic discourse. The architect of worlds had given us the blueprints for questioning everything. But blueprints are just the beginning. To understand whether we might actually be living inside a simulation, we need to examine the evidence. And that evidence comes from the most unexpected corners of science. In 1972, Pong appeared on arcade screens, two white rectangles bouncing a square dot back and forth. The entire game consisted of roughly 300 lines of code. Players marveled at this primitive digital tennis match, never imagining they were witnessing the first step toward simulating reality itself. Fast forward 50 years. Today's video games render photorealistic humans with individual hair follicles, realistic skin textures, and believable emotional expression. Characters exhibit complex behaviors, remember past interactions, and respond dynamically to player choices. What happened between Pong's simple rectangles and today's digital actors? The answer lies in humanity's most reliable prediction about the future: Moore's Law. In 1965, Intel co-founder Gordon Moore noticed something extraordinary. Computer processing power was doubling approximately every 18 months, and this exponential growth showed no signs of slowing. Moore predicted this pattern would continue, and for nearly 6 decades, he's been remarkably accurate. The smartphone in your pocket possesses more computational power than the supercomputers that he's been remarkably accurate. The smartphone in your pocket possesses more computational power than the supercomputers that guided Apollo missions to the moon. But exponential growth is deceptive to human intuition. We think linearly, expecting steady, predictable increases. Exponential curves start slowly, then explode upward in seemingly impossible ways. Consider this. If you fold a piece of paper in half 42 times, the resulting stack would reach the moon. That's exponential growth. Unimpressive. Initially mind-bending ultimately. Our computational capabilities are following this same trajectory. In 1981, IBM's first personal computer had 16 kilobytes of memory. Today's high-end gaming computers have 32 gigabytes, 2 million times more capacity. Graphics processing units now perform trillions of calculations per second, rendering complex, three-dimensional worlds in real time. And we're just getting started. Quantum computing promises to shatter current limitations entirely. While classical computers process information as binary digits, ones and zeros, quantum computers exploit the strange properties of quantum mechanics. They can exist in multiple states simultaneously, potentially solving certain problems exponentially faster than any classical machine. Google's quantum computer recently performed a calculation that would take the world's most powerful supercomputer thousands of years to complete. The quantum machine finished in minutes. As these systems mature, they'll tackle problems currently beyond imagination, including, perhaps, simulating conscious beings indistinguishable from real ones. But how much computational power would that require? Researchers have attempted to calculate the processing requirements for simulating a human brain. The numbers are staggering, but not impossibly large. The human brain contains roughly 86 billion neurons, each connected to thousands of others through synaptic networks. Every thought, every memory, every sensation emerges from electrical and chemical signals flowing through this biological computer. Neuroscientist Henry Markram estimates that perfectly simulating a human brain would require roughly 1 exaflop of computational power, 1 quintillion calculations per second. That sounds enormous. But context matters. The world's most powerful supercomputers already approach this threshold. China's Tianhe-3 system performs over 1 quintillion calculations per second. We're not centuries away from brain-level simulation. We're potentially within decades. However, simulating consciousness might not require perfect neural replication. If we only need to reproduce the emergent properties of thought, the subjective experience of being conscious, rather than every molecular interaction, the requirements could be dramatically lower. Some researchers suggest that simulating human-level consciousness might require only the computational power of today's high-end gaming computers. This possibility becomes even more intriguing when we consider that simulated beings wouldn't need the same biological constraints as real humans. A simulated person could exist without modeling every cell, every protein interaction, every quantum mechanical process occurring in a biological body. They would only need sufficient detail to maintain the illusion of authentic experience. The implications are profound if current trends continue. Consumer-grade computers might soon possess enough power to run conscious simulations. Every college student, every hobbyist programmer, every curious researcher could potentially create digital beings with rich inner lives. The number of simulated minds could explode exponentially, dwarfing the population of biological consciousness. Consider the trajectory from Pong's bouncing square to photorealistic characters, from 16 kilobytes of memory to quantum computers performing quintillion calculations per second, from simple arcade games to virtual worlds indistinguishable from reality. If this exponential curve continues for just a few more decades, the computational resources required for perfect simulations will become as commonplace as today's smartphones. But there's an unsettling corollary to this technological progress. If we're approaching the threshold for creating conscious simulations, then other civilizations perhaps centuries or millennia ahead of us, have likely already crossed that line. They possess computational resources that make our most powerful supercomputers look like pocket calculators. Such civilizations could run millions, billions, perhaps trillions of ancestor simulations, each populated by billions of conscious beings who believe they're living authentic lives. The mathematical implications align perfectly with Bostrom's trilemma. Simulated beings would vastly outnumber real ones, making our own simulated existence statistically likely. The exponential curve that gave us smartphones and video games might also explain why you're probably not real. Every technological milestone, every doubled processor speed, every leap in computational capability brings us closer to a universe where artificial consciousness becomes indistinguishable from the authentic variety. We're not just observers of this technological revolution, we might be products of it. And the evidence supporting this possibility comes from realms even more fundamental than computing power. It emerges from the very structure of reality itself. At NASA's Jet Propulsion Laboratory, a scientist named Rich Terrile spends his days analyzing data from distant galaxies and designing missions to explore alien worlds. But Terrile has become obsessed with a different kind of exploration, one that might prove our entire universe is artificial. Terrile isn't a fringe theorist. He's a respected planetary scientist who helped design the imaging systems for the Voyager missions. Yet he's convinced we're living inside a computer simulation, and he's developed specific experiments to prove it. His approach is elegantly simple. If our universe is computational, it must have computational limits. Find those limits, and you found evidence of the simulation. The search begins at the quantum scale, where reality becomes truly bizarre. In quantum mechanics, particles don't have definite positions until observed. They exist in probability clouds called wave functions. To Terrile, this sounds suspiciously like a computational trick. Why would a simulation waste processing power calculating the precise location of every particle? When no one's looking, better to store approximate probabilities and only compute exact values when observation forces the calculation. This leads to Terile's most provocative hypothesis. Quantum mechanics isn't fundamental physics. It's computational efficiency, the uncertainty principle. wave-particle duality, quantum entanglement. These might all be artifacts of how our simulated reality processes information. We're not discovering the deepest laws of nature. We're reverse engineering someone else's programming code. Testing this idea requires extraordinary precision. If space-time is truly digital, it must be composed of discrete units, quantum pixels, essentially. At the smallest possible scale, called the Planck length, space itself might become grainy rather than smooth. Advanced experiments are now probing these microscopic distances, searching for evidence of underlying pixelation. The Large Hadron Collider, originally built to discover exotic particles, has been repurposed for simulation detection. When particles collide at near-light speeds, they probe space-time's structure at unprecedented resolution. If reality is digital, these experiments should eventually reveal the cosmic pixels. So far, space appears smoothed down to scales 10 billion times smaller than a proton, but researchers are pushing toward even more extreme measurements. Meanwhile, other scientists are hunting for computational glitches, moments when the simulation's processing power becomes overwhelmed. Astronomer John Barrow suggests looking for sudden changes in fundamental constants. If our universe is running on finite, computational resources, periods of high complexity might cause the simulation to adjust its parameters to maintain stability. Stars, galaxies. Even the speed of light itself might fluctuate as the cosmic computer struggles with processing demands. MIT's Seth Lloyd has proposed a different approach. Exploit the simulation's memory limitations if our reality is computed. Past events must be stored somewhere, but infinite storage is impossible. So the simulation might compress historical data, keeping only essential information and discarding details no one remembers. Lloyd suggests coordinated experiments where researchers simultaneously record precise measurements of quantum systems across multiple locations. If the simulation can't maintain perfect consistency across all observations, discrepancies should emerge. The most ambitious search involves testing computational speed limits. Physicist Silas Bean realized that simulated spacetime would have a maximum resolution, a cosmic frame rate, essentially. High-energy particles should behave differently if they're constrained by digital processing speeds. Bean's team analyzed cosmic ray data, looking for energy cutoffs that might indicate computational boundaries. They found intriguing anomalies in the highest energy particles, though the results remain inconclusive. But evidence hunting faces fundamental obstacles. The most sophisticated simulation would anticipate these detection attempts. Advanced programmers could build in countermeasures, fake quantum mechanics that mimic continuous space-time, artificial glitches designed to mislead investigators, or dynamic adjustments that eliminate computational signatures whenever someone looks for them. Worse still, the simulation might have unlimited computational resources from our perspective. If our simulators exist in a universe with different physical laws, perhaps one where information processing costs nothing, then resource limitations wouldn't create detectable signatures. We might be looking for evidence that doesn't exist because the simulation operates under constraints we can't imagine. There's also the observer problem. If we're simulated beings, our scientific instruments are simulated too. How can artificial detectors find evidence of their own artificiality? It's like asking whether characters in a video game can discover they're digital, the game's physics engine will show them exactly what the programmers intended. Nothing more. Some researchers have reported intriguing preliminary results. Teams at Fermilab detected unexpected noise in their most sensitive gravitational wave detectors, a persistent background hum that might represent the simulation's computational substrate. NASA's Kepler Space Telescope found statistical anomalies in stellar brightness measurements that don't match any known astrophysical process. These could be glitches, but they could equally be unknown natural phenomena. The search has also revealed how difficult it is to design definitive tests. Every proposed experiment has loopholes. Every anomaly has alternative explanations. The simulation hypothesis is scientifically frustrating because it's nearly unfalsifiable. It can accommodate almost any evidence by adjusting assumptions about the simulator's capabilities and intentions. Yet, the hunt continues, driven by a recognition that the stakes couldn't be higher. If simulation theory is correct, it revolutionizes our understanding of existence, consciousness, and humanity's place in the cosmic order. If it's wrong, we're still learning profound truths about reality's deepest structure. Recent developments suggest the search is accelerating. Multiple research teams are now dedicated specifically to simulation detection. Government agencies have quietly funded related projects. Tech billionaires are bankrolling ambitious experiments. The academic skepticism that once surrounded simulation theory is giving way to serious scientific investigation. Rich Terrell believes we're close to answers. His latest calculations suggest that if computational signatures exist, current technology should detect them within the next decade. Other researchers are less optimistic, arguing that definitive proof might require centuries of technological advancement, or entirely new theoretical frameworks. But perhaps the most unsettling possibility is that we're asking the wrong questions entirely. The evidence hunters assume they can detect simulation signatures through clever experiments. They might discover instead that the question itself, are we simulated, reveals something far more profound about the nature of reality, consciousness, and what it truly means to exist. When Elon Musk stepped onto the stage at Recode's 2016 conference, the audience expected him to discuss electric cars or space exploration. Instead, he delivered one of the most provocative statements in modern philosophy. The odds that we're living in base reality, 1 in billions. Musk wasn't hedging. He wasn't speculating. He spoke with the absolute certainty of someone who'd solved a mathematical equation. According to the world's most successful technology entrepreneur, you are almost certainly a digital simulation, and anyone who believes otherwise is deluding themselves. His reasoning was elegantly simple. Video games improve exponentially. Conscious beings will eventually create perfect simulations. Therefore, simulated beings must vastly outnumber real ones. This wasn't casual speculation from a tech celebrity. Musk has reportedly invested millions in research aimed at breaking humanity out of its digital prison. He's not alone among Silicon Valley's elite. PayPal co-founder Peter Thiel funds simulation detection research. Google's AI researchers seriously discuss the probability that artificial intelligence might discover it's living in a simulation. These are people who build our thing in a simulation. These are people who build our technological future, and they're convinced that future has already arrived. But across the academic divide, philosophers and physicists are pushing back hard. Harvard cosmologist Lisa Randall dismisses simulation theory as a waste of time, arguing that unfalsifiable hypotheses belong in philosophy departments, not science labs. She points out that simulation advocates can explain away any contradictory evidence by adjusting assumptions about the simulator's capabilities. A theory that can accommodate any possible observation isn't a theory at all. It's a belief system. MIT physicist Max Tegmark goes further, calling simulation theory pseudoscience dressed up in mathematical clothing. He argues that simulation advocates commit a fundamental error, assuming consciousness can be perfectly simulated, without understanding what consciousness actually is. We don't know how subjective experience emerges from physical processes, so claims about simulating consciousness are premature at best, meaningless at worst. The skeptics raise devastating logical objections. If we're simulated, why would our simulators allow us to discover simulation theory? Wouldn't they program us to believe in the reality of our world? And if they wanted us to question our reality, what purpose would that serve? Either way, our beliefs about simulation become meaningless, determined by our programmers rather than rational analysis. Oxford philosopher Nick Bostrom, who originally formulated simulation theory, finds himself defending against both camps. True believers like Musk misrepresent his argument, claiming he proved we're probably simulated, when he actually demonstrated that one of three possibilities must be true. Meanwhile, critics accuse him of abandoning scientific rigor for philosophical speculation, despite his careful mathematical reasoning. Yet simulation theory's appeal transcends logical arguments. In an age of artificial intelligence, virtual reality, and social media-mediated existence, the idea that reality itself might be artificial resonates powerfully. We spend increasing portions of our lives in digital environments, interacting with artificial intelligences, questioning whether online personas represent authentic selves. Simulation theory offers a framework for understanding our increasingly synthetic existence. The psychological appeal goes even deeper. Traditional religion promised that earthly existence wasn't the ultimate reality. There was something greater beyond. Simulation theory provides a secular version of transcendence. Instead of heaven, we have base reality. Instead of gods, we have advanced programmers. Instead of divine purpose, we have computational objectives. For people who find religious explanations unconvincing, but still crave meaning beyond material existence, simulation theory fills a spiritual void. This explains why the debate generates such passion. For believers like Musk, simulation theory isn't just a hypothesis. It's a call to action. If we're trapped in artificial reality, we should work to escape, or at least contact our simulators. The urgency becomes existential. Should we focus on colonizing Mars if our Mars isn't real? Should we worry about climate change in a simulated environment? Skeptics see dangerous pseudoscience masquerading as rationality. They worry that simulation theory encourages nihilistic thinking. If nothing is real, why does anything matter? They point out that previous generations embraced equally compelling but ultimately false theories about reality's nature. The appeal of an idea doesn't make it true. Surprisingly, some religious thinkers find themselves allied with tech billionaires against academic materialists. If reality can be layered, simulations within base reality, then materialist. Assumptions about the primacy of physical matter become questionable. Both simulation theorists and religious believers accept that fundamental reality might be radically different from apparent reality. The debate reveals deeper fractures in how we understand truth itself. Scientists demand falsifiable hypotheses and empirical evidence. Philosophers embrace thought experiments and logical reasoning. Tech entrepreneurs trust exponential trends and computational analogies. Religious believers prioritize revelation and spiritual insight. But perhaps the most unsettling aspect of the simulation debate isn't the disagreement between smart people. It's the recognition that our position on this question reveals something profound about our worldview. Do you trust empirical evidence or logical reasoning? Do you believe consciousness is computational or irreducibly mysterious? Do you think reality is fundamentally material or ultimately informational? Your answer might say less about simulation theory than about who you are. Look in the mirror again. The same face stares back. But now you carry a different question. Are those eyes real? Or are they pixels rendered by some unimaginably sophisticated computer? Does it matter? This is where simulation theory leads us, not to answers, but to a transformed relationship with uncertainty itself. We may never know whether we're biological beings on a spinning rock or digital constructs in someone else's machine. The evidence remains inconclusive. The experiments continue. The debate rages on between brilliant minds who can't agree on the nature of existence. But perhaps that's exactly the point. Zhuangzi never resolved his butterfly dream. He didn't need to. The question transformed his understanding of identity, consciousness, and reality's fluid boundaries. Whether he was a man or a butterfly became less important than recognizing the arbitrary nature of those distinctions. The dream taught him something precious. Certainty about fundamental reality might be impossible, but wisdom lies in embracing that impossibility. If we're living in a simulation, does your love feel less real? Do friendships become meaningless? Does art lose its beauty? The answer reveals something profound about what we value. If authenticity depends on substrate, carbon versus silicon atoms versus bits, then we've misunderstood authenticity entirely. Your consciousness experiences joy, pain, wonder, and loss. These experiences shape who you are, regardless of their underlying implementation. A simulated sunset can still move you to tears. Digital music can still stir your soul. Virtual relationships can still break your heart. The substrate might be artificial, but the experience remains undeniably real. This paradox points toward a deeper truth. Reality isn't about the material foundation of existence. It's about the meaning we create within whatever framework contains us. Whether we're biological or digital, our choices still matter to us. Our relationships still define us. Our struggles still shape us. The question isn't whether we're real, but how we choose to live within whatever reality we inhabit. Simulation theory forces us to confront the limits of knowledge itself, like Descartes contemplating his evil demon. We discover that absolute certainty about external reality might be forever beyond our reach. But this doesn't lead to nihilism. It leads to a more mature relationship with existence. We can live fully without knowing everything. We can love deeply without proving our authenticity. We can seek truth while accepting that some questions might remain forever unanswered. The simulation hypothesis will likely define philosophical discourse for generations to come. As our technology grows more sophisticated, as artificial intelligence becomes more convincing, as virtual worlds become indistinguishable from physical reality, the question will become increasingly urgent. Are we the last generation of purely biological consciousness? Or are we already digital beings, wondering about our origins? But maybe the question itself is more valuable than any answer we might discover. In forcing us to examine the nature of reality, consciousness, and existence. Simulation theory returns us to philosophy's most essential purpose, learning to live wisely in an uncertain universe. Whether we're real or simulated, that wisdom remains our most authentic achievement.